of the Iowa Local Technical Assistance Program. There are 51 of us around the country, all states plus the Puerto Rico. Peter, you are unmuted, in case you didn't know.
Yep.
Yep. So I'll do a little bit of an introduction here and let people know what Iowa LTAP does. But if, again, I was going to say if you can't hear me, there's not much I can do if they can't hear me. I will do a little bit of chatting to let people know. If you've signed in with your first name, again, and not your full name, you'll want to chat with me or send me an email so that we know your full name so we can send you certificates of attendance. We are a state-based local technical assistance program. We do not go out to other states and get approvals. We send certificates of attendance. It's up to the attendee and their responsibility to know whether the certificate applies with where they are or not. You're going to want to also, of course, put some notes down that it was an hour and what the subject was and things like that, because for an hour webinar we do not have an agenda or anything like that. But we do not have, we don't track people's PDHs and things like that. So you gotta know your own rules, right? Because I know we have a lot of people from Florida on board, a lot of people from Washington, basically outside the state of Iowa. So just be aware of that. So you are muted on entry. If you want to ask a question of Peter, you're welcome to use the chat pod. If you can't see your chat pod, please click the icon at the upper right if you're on a regular laptop, or go to the view drop-down menu and pull that up, and you can chat with me either privately or you can chat publicly. Now, none of the recording that we're doing records the attendee list or the chat pod or anything like that. So we do our best to get certificates of attendance out to those that let us know. So I will be checking that chat pod the entire time Peter is talking. What will happen when Peter comes on board and shows his full screen is your chat pod will disappear. But there'll be a tab at the top of your computer if you're using a regular laptop, or a tab somewhere on your screen that allows you to pull a drop-down menu out that has a chat pod icon on it. That'll allow you to reactivate your chat pod so you can ask questions during the presentation. The other note, of course, is if you got other people, let me know. And again, I'll do my best to send things out. It'll go to the email address that's on record. And again, if we can't figure out who you are or don't have your email address, we can't send a certificate. If you are one of what I'm now calling webinar pirates and you've gotten a link from something other than our registration, then you definitely will have to email us, email me at knap@iastate.edu so that I know you're on board, because all that WebEx records is when people come on and off and what's in the attendee list. So we're at about 38. I think we've stabilized a bit here. I did want to mention a few other things. Next week we are going to have a webinar on building intelligence for next generation traffic management. Another 1 hour on the 10th. On the 15th, we're doing leadership skills, team and group development, and self-assessment, organizational self-assessments. On the 16th, we're doing a local agency perspective on automated traffic signal performance. On the 23rd of July, we have a webinar on improving work zone safety, temporary rumble strips, smart arrow boards, and other connected devices. And finally, on August 7th, we have recent advances in heated technology for a 1 hour webinar. I'd also welcome everyone to register if they are interested. There's a National LTAP Association conference that's virtual this year from the 28th to the 30th of July, and all are welcome. Just go to nltapa.org and hit the conference drop-down menu, and the registration button will be there. So without further ado, I'm going to pass this over to Dr. Taylor. Peter is the director of the National Concrete Pavement Technical Center, an internationally recognized center that does research in concrete. And Peter, we're actually seeing my welcome right now. I am. So go ahead and share your screen.
It's interesting.
Yeah. So all right. So let me hold on. Let me. I'm trying to find my mouse here. Yeah, we have not had this problem before. Let me try this. Let me get rid of it. Oops. Something new each time. go ahead and try it now.
Nope, it's not giving me an option now.
Okay, so I'm going to take it back, and we'll try it again. Wait for it. What about now?
Still blank.
What do you mean blank? Sorry.
When I hit the view button, all the options are grayed out.
Yeah, so all I can guess is that at some point, for some reason, we lost connection. This is the first time this has ever happened.
Should I jump off and get back in?
So why don't you try to jump off and come back in, and we'll try that. Thanks. I apologize for this, folks. We actually had tested this, and it was working half-hour ago. So we will continue to, we'll give it a shot here. Because this is in the cloud, sometimes things get disconnected. So we'll see what's going on. And again, with all the devices that are out there now, not every software is able to figure out every device that's out there. So sometimes there's a little bit of confusion. There he is. Okay. Okay, Peter, can you hear me?
Yep, and I'm still not able to show my screen.
Can you send me?
Wait, there we go. There we go.
There we go. Hey, folks, we're there. So for those of you that go ahead, you're sharing. You need to share the other monitor. So you're going to have to stop sharing. Hopefully it works. There we go. So just before you get started here, Peter, everyone, now you're looking at full screen. You need to scroll to the top of your screen by the blue tab and hit the chat pod, and that will open your chat panel up again so you can ask questions while Peter is talking. Peter, if you want to reintroduce yourself and give some background, that's great.
All right. Thank you very much, Keith, and thanks for the opportunity. And thanks to everybody for signing on. It's first week in July. It's been a very interesting first 6 months of our year. It's a long weekend coming up, and we're all in holiday mode. So we'll try and keep this light, but educational and interesting. I'm targeting an audience of people that don't regularly deal with concrete. So I'm going to be keeping things pretty, hate to say simple, but I'm not going to get too far into the weeds. But just to sort of pique some curiosity, remind you of stuff you probably never learned in college about what concrete is. I'm the director of the Concrete Pavement Technology Center here at Iowa State. I'm a materials geek, worked in industry, worked in consulting, was born and raised in Central Africa. That's why the rest of you speak funny. And all right, let's do this. Everything you wanted to know about concrete, but we're afraid to ask. I do have an agenda, 4 items. What is concrete? No, really, what is concrete? And then we'll get into a little bit of the details about what forms concrete and why I think it is fascinating. And then looking forward, talking about some of the current research and activities we're doing to make better concrete so that it lasts like it should and that agencies are getting the best value for their money, whether it's in vertical construction or pavements, slabs on grade. Okay, the first quiz question for those who need it. This is not a cement truck, and it scares me how often in lay circles I hear people refer to one of these as a cement truck. At the same time, it scares me more how many practicing engineers refer to it as a cement truck. My daughters would be able to tell you that this is indeed a transit mixer, more popularly or commonly known as a ready-mix truck. And we'll get into a couple more detail about that a little bit later. All right, so the prevailing perception of concrete, the first thing that many people will say is, yeah, it's strong. And indeed it is. This is a structure built on the coast of Norway during World War II to keep the nasty British from invading. And that structure is still there. Locals are now using them for residences and all sorts of interesting activities. That concrete is going to be a monster to remove. is indeed very strong. There is a whole family or class of architecture called brute architecture, and this structure in Chicago is very typical. And normally when you have brute architecture, concrete's at the heart of it. It's also considered to be pretty boring. Now, I look at that photograph and I get really excited because there's no damage, there's no cracks. It's actually a really beautiful piece of pavement. And boring is good because it means we don't have to fix it, we don't have to work on it, I don't have to get called in to consult on it. This is good stuff. What it does mean is that we can drive on it with safety and reliability, and that's a good thing. Sometimes concrete cracks. No, wait. Be aware that concrete always cracks. The art is defining where that crack forms in a way that is controlled and desirable. But almost any piece of concrete, you put it under a microscope, you're going to find a crack somewhere. A war story about the image on the right is plastic shrinkage cracking in a parking lot in the building next door to mine. I was out there getting this photograph about a year ago, and the lady came out of the building and was beating me over the head with her umbrella because she was extremely sensitive to the fact that I was taking photographs of her car, the shadow of which is in the top of the photo. And she had a very hard time believing that I was taking photographs of concrete. Now, my family are completely used to this, driving along the road, suddenly stop, pull over, jump out, take a photograph of the road. Yeah, that's what I do. All right. The other rap that concrete gets is that it's a significant impact on carbon footprint on the planet. It is. Producing concrete, using concrete does generate a fair amount of CO2. The point to note that, though, is that the efficiency is such that compared to other materials, it's probably a little bit better. The reason concrete contributes so much to global CO2 production is because we use so much of it. So even if we were generating relatively little, because the volumes are enormous, the contribution adds up pretty quickly. And again, I'll talk about how we're trying to address that a little bit later on. Okay, so those are all the negatives, all the things that the everyday person thinks about what concrete is. Now is when I start to be an evangelist and present an alternative point of view. So, what is concrete? It's the stuff you've seen, or it's the backbone of civilization. Photograph on the left is extracted from Iowa DOT archives. I would hate to commute on that every day, and so would you. And so the fact that we can provide hard, safe, plowed, reliable surfaces for our vehicles is not trivial, especially when we're trying to go long distances, when we're trying to haul large volumes of materials. Look on the photo on the right. Very pretty, very scenic, could easily be reasonably close to where I grew up. In a way, it's kind of romantic. You think, hey, look, no traffic, no skyscrapers, no pollution. But then look a little bit closer. The young lady in the foreground. Look at her dress. Think about her potential for education. Think about how she would get medical attention when she needs it. How is she going to get to school? How are we going to provide water to where she lives? Without concrete providing the guts of the infrastructure, and civilization would end. So without concrete, civilization, as we know it, I will argue pretty strongly, would be in a very different place. Again, some more images. This image on the left, a water tower near where I used to work in Johannesburg. Not only is it pretty, it's functional. It's providing water to a very large city. On the right, CN Tower in Toronto. Once again, your television, your entertainment, your cell phone connections that your kids can't live without, all coming through structures such as this, built out of concrete. can be also very elegant, very beautiful. Image on the left, one of my favorite bridges on the south coast of South Africa. Now, in that part of the world, it's one of the most scenic and beautiful drives that you can follow. The only problem is that every 10 miles or so, there's a very deep ravine of the river finding its way to the sea. And it was not that long ago where you had to take huge diversions inland to get over the river because these gorges were pretty deep and steep. And then the country started to build bridges such as this. And all of a sudden, we took an hour off the drive between two neighboring cities. They're also pretty. This bridge is actually one of the best bungee jumping sites on the planet. It's one of the highest and most extreme bungees. So if you want details of how to get there, call me. I'll happily let you know. Image on the right, I just found that when I was noodling around looking for stuff to fill this slide set. And to me, that's rather cool. It's kind of crazy. I think it comes out of France somewhere. That's somebody's home, and they built it out of concrete, and it's really interesting. All right. What about other applications? Well, both of those vessels are concrete. During World War II, they ran out of steel to build Liberty ships, so they started building them out of concrete. There was, I think, about a dozen Liberty ships built out of concrete. Most of them have since been scuttled and being used as fish havens. One of them in the harbor of Galveston City in Texas. But again, very functional, survived the corrosion environment, and provided a useful service during World War II. The one on the left is a home-built concrete yacht. Guy, I think he's out in Norway, has built the structure and having a lot of fun with it. Not only is concrete gray, cracked, and boring, functional, useful, can also be really beautiful. The building on the right is the Baha'i Temple in Chicago, well worth a visit next time you go there. In the center, a home built out of thin concrete shell elements. And on the left is a structure that's going into a portion of the Hudson River in New York City, where they've built these basic pods out of precast concrete, and it's become almost an island off the mainland. And it's going to become a park, a band shell, basically a place for people to hang out and chill out very close to Manhattan in New York. Now, the trick question is whether COVID will ever allow us to get there, but it's a very interesting concept. It's still under construction. It should be really intriguing. And the architecture behind that is fascinating. All right, it's also durable. Once again, we have one of these long gray stripes of concrete that's really, really boring, but boring is good. This piece of concrete is more than 100 years old. It is one of the oldest piece of roadway built in Iowa out of concrete. Admittedly, it doesn't get a lot of traffic. It's an access road to a cemetery, so most of the traffic is one way. But it hasn't been touched or treated for a long time, and it's still sitting there under traffic. There's a photo I took probably 3-4 years ago. The other interesting thing about concrete is that, again, our standard perception that it's a gray powder you mix with a bit of water and rock and sand, and it sets and gets hard and cracks and holds things up. All of which is true, but the detail behind that is extraordinarily detailed. The photo on the left is a textbook that I make all of my PhD students read and understand. So, you know, their lives are not trivial. All of us that hate chemistry, yeah, we actually do have to get into it a little bit to understand the material as rigorously as we should. The photo on the right, look at the scale, 2 micron for about a quarter of the image of fresh calcium silicate hydrate fluff. That's the stuff that's holding up civilization, is that fluff. And again, the understanding how that's forming, what it's made out of, and how to protect it is an intriguing study. Okay, so just some terminology. Cement and water together mixed up makes paste. Paste is basically glue. Paste mixed with fine aggregate makes mortar, and that's what we use to make stucco, to glue bricks together. Mortar plus coarse aggregate forms concrete, stuff I've been waxing lyrical about for the last few minutes. But again, when you get down into the detail, it's intriguing. This is a photograph of a single cement grain. Now, considering that cement as delivered is typically about the same fineness as baking flour, that particle is very, very small, 10 micron across. And you can see this has been polished and is being looked at through a polarizing microscope, and all these pretty colors jump out. And you can see that there are a number of different compounds, and each of these compounds, the ratio of them affects how the system performs. Some of them react very quickly, some react slowly, some of them are challenging in the way they react, and others just sit there and look pretty and change the color. Again, the detail is really intriguing, and I've got a 90-minute presentation built around this slide. If anybody wants to phone me, we can work through it. One of the points to note is that the chemistry of cement, Portland cement, is changing and has been over time since the 20s. The two basic compounds, C3S and C2S, and this, I'm not going to get into the weeds of the chemistry. C3S is increasing, C2S is decreasing. Why? Because the C3S, the red line, is the stuff that makes cement set and hydrate faster. It gets stronger faster. And that's driven by the construction industry, because we don't want to wait for this stuff to get strong. We want to be able to drive on it. We want to be able to build the next floor. We want to be able to occupy the building sooner. And so the cement industry is responding to pressure from their customers to make this system faster and faster. And I'll talk a little bit about some of the negative side effects in a couple of slides. Just a way to visualize what's happening here. You put water and cement. Here we have two cement grains floating around in a bucket of water. They go through a chemical reaction. It's not just a wetting and setting and drying. It's not like mud. You don't put it out in the sun to bake and get hard. It's actually a chemical reaction with the water. So that reaction starts to form little fingers that grow out of the cement grains. When these fingers mesh and interact with each other, it stops being a liquid and becomes a solid. If you keep the reaction going by continuing to provide water, eventually it fills up and becomes a dense, strong, impermeable, solid material. If you stop the water, if you let it dry out too soon, you'll be living with this system, not as strong, not as impermeable, not as durable. And so when I start nagging people about the need for curing, which is to keep the concrete wet and to keep the concrete warm for as long as possible, that's because I want to get to this state. We're getting the most out of our cement. All right. Another compound or family of compounds that we've been using in great abundance are the so-called supplementary cementing materials. Typically in Iowa, we use fly ash. Near Chicago and on the East Coast, slag cement is reasonably accessible and common. We can also put in natural pozzolans. This is a metakaolin out of Georgia. And then in specialized applications, we can throw in silica fume. And all of these change the performance of the system, generally for the better, and we put them in for good reason. Okay, this slide is all of the chemistry you're going to get. Yes, I know it's July 2, and you all hate chemistry. So do I. I failed it at high school. Don't worry, you will survive the next 3 minutes. Cement and water combined together go through a chemical reaction to form two different compounds, calcium silicate hydrate. Those are those fingers, the bits that mesh and make concrete strong. The byproduct is calcium hydroxide. These are hexagonal, and that's why I've drawn this image like this, hexagonal crystalline particles. Now remember, the crystals actually are not that strong. They're not tough. They're not able to resist cracking. Old-fashioned cements, the ratio of CSH to CaSH was about as illustrated here. Modern cements, we're getting far more calcium hydroxide. Now, as I said, the calcium silicate hydrate, the CSH, is the good stuff. Calcium hydroxide is, it's not bad, but it's not truly beneficial to the system. And so the modern cements, the ones with the high C3S, that red line on the top of the chart that was growing 2-3 slides back, this CH is increasing. And so we're incorporating more and more of this less good stuff into our mixtures. The way to deal with that is with supplementary cementing materials, fly ash, slag, the stuff I just talked about. Again, add them and water. They combine with the calcium hydroxide to magically form, hey presto, more calcium silicate hydrate. And so we're turning this not so good stuff into really good stuff with the use of the slags and the fly ashes. So when you come across engineers who look at you and say, don't contaminate my cement with that nasty waste product from other people, it's not actually true. It's more than it is someone else's waste product, but it's having an active, beneficial part of the process of making really good concrete. It's there for a purpose. And in fact, now with fly ash getting harder and harder to acquire, we're having to sort of go back and think about, well, what other supplementaries are out there that we can use to replace fly ash to still achieve this, the benefits that we've been talking about. All right, just a quick word on the effects of supplementaries. They will delay the final set. Now, in summer, that's a good thing because in many cases, the concrete will set too fast. In winter, that's a bit of a challenge. They will reduce the heat peak. That's good because that actually has a fairly large impact on when the cracks form and how big they are. It reduces or changes the heat generation as it slows down that heat generation, which is fantastic for things like mass concrete, bridge piers, dam walls. We want to keep the system cooler, again, because of trying to control cracking. The real huge benefit is that we reduce permeability. Now, all of the things that attack and eat concrete and make it look bad after time involve water getting into the system. If we can keep the water on the outside, we buy time. And by reducing the permeability of the system, we're doing just that. So it's an extremely desirable factor that we're trying to get into. It increases strength. Yeah. Everybody lives and dies by strength. But like any good medicine, there are side effects. Last night, watching TV, image of family happily dancing down the beach, promising to live forever and be eternally happy because they took some drug with a strange 3-syllable name. And then you go with a deep, at the end of the advertisement, you get the guy with the deep voice talking really fast, listing all the negative side effects. And it's kind of scary how often those side effects include death. Fly ash doesn't kill your concrete. It actually makes it better. But you do have to account for things like slower strength gain initially, slower setting. But once we've learned how to deal with those, we're actually making better concrete at the end of the day. The side effects are overwhelmed by the beneficial effects of why we put it in. Okay, I've talked about fly ash, I've talked about cements. What else goes in a mixture? Aggregates, the rock. Why do we put it in? Well, it's basically because rock is a whole lot cheaper than cement. Rock is also more dimensionally stable. It doesn't shrink over time. It's done that through aeons as the rocks have been settling down inside our planet. The part that people don't really get is that aggregates have a relatively small effect on the hardened performance of concrete, but they do have a fairly large effect on the fresh properties. One of the things that we pay attention to is the gradation, how much of the coarse stuff and how much of the fine stuff. And the fundamental, simple idea to think about that is that the blue square here is the same size as the blue on the left-hand image. The blue square on the right-hand side is the same size as the blue in the second, the other image with the fine aggregate in it. You can see that by putting in a graded system, you leave less space behind. Why is that a good thing? Well, again, we're trying to get as much aggregate into the system as is reasonable because the cement is the expensive part, and it's the part that shrinks. So the fine art of mixture proportioning is in controlling this aggregate gradation to keep the size of this blue block about where we want it. And I'll talk about that more in a few slides. The other big aspect in construction is that the state of absorption of the aggregate will affect the workability. If you're working with a stockpile, it's dry, you're going to have to add extra water to keep your workability. If the stockpile is wet, you're going to need to add in less water to compensate for the excess water that you're in putting into the mixture because it's coming out of this stockpile. And it's a case like this where you've got a huge mixture. The guy driving this vehicle is probably the best, should be the best paid person on the construction site, because he can strongly affect the workability of the system and the uniformity of the system, and indeed the long-term performance of that concrete. Why? Because the thing that controls everything about our concrete is the water-cement ratio, the ratio of water and cement. That's what governs all of our properties. So knowing where your water is coming from, whether it's coming from the batching with the aggregates and the admixtures added later, like in this photograph, has a very strong effect on the performance of your system as a whole. The reason I have this photograph is that when we go to the next slide, that's that same slab. That is 6 months after it was placed. Because this crew had been having such a lot of fun adding water into the mixture to make it more workable, they destroyed all of the durability of that system. And literally 6 months later, this thing had to be taken out of service again and replaced. It's not trivial. If you see people adding water to your concrete, stop and panic, because it may be increasing workability, but it's affecting strength, shrinkage, and permeability and durability. And I know it's an everyday statement. Every time a ready-mix truck arrives on a construction site, the first thing that the foreman says, without even looking up, is add 10 gallons. I'm doing everything I can to discourage you from doing that. Get the workability right at the batch plant. Avoid adding the extra water. So then you've got control of what's actually being put in the ground. And yes, I know there's some caveats with that in terms of loss of workability during hauling, hot temperatures, drying out, evaporation, and all of that good stuff. But you know, excess water is bad. If you absorb nothing else out of today's rant, absorb that. Other products we put in are chemical admixtures. We put them in to control the workability, to make it easier for the crew to handle the stuff. That's how you get the improved workability, not by adding water. It affects, we can put in admixtures to control setting, the air void system, viscosity, corrosion inhibitors, water reducers. There is a whole family of products. The biggest thing I would say about admixtures, they're great. They do wonderful things for our mixtures, but don't use them to fix bad concrete. Make good concrete and then make it better, make it really great by adding in these admixtures to get the final polish, the cherry on top for these properties that you're really looking for. All right. Again, just a couple of images of, look at the scale of concrete. You know, engineers are used to thinking in terms of fairly big things, meters high, meters wide. Burj Dubai Tower, I think one of the highest buildings in the planet, Kariba Dam, where I grew up, one of the top, it's got that, a significant amount of concrete in that structure, built in the 50s, and still serving the system very reliably. Big stuff. All right, we can then start to go down in scale, 40 millimeters across, an inch and a half, and you start to see the detail. You see the coarse aggregate, the fine aggregate, the air bubbles, the variety of the aggregates we've got in the system. Put it under an electron microscope, and you see even more detail, the little fingers of calcium silicate hydrate, unhydrated fly ash particles, and the air voids from early age concrete that hasn't been well cured. This is a sample that was cut open at 4 days, so it's not fully hydrated yet. Go into even more detail, 15 micron across, and again, we're still not seeing all of the detail. So the deeper and deeper and deeper you get into the system, the more interesting and entertaining it gets to be. Why do we fuss with being so excited about understanding the details? Well, when I was an undergrad student, this was a poster that most of us engineering students had on our dorm walls. The message being, we're here to learn how to prevent this sort of thing. My brother, who was a professor at the time, had a variation on that poster. If you learn nothing from anybody's mistakes, you're going to make them again for yourself. So if you make a mistake once, yeah, we can sort of almost live with that. If you make a mistake twice, no, you're in trouble. And so, again, we should be learning by looking backwards from the world around us. How do we design things? The art of what we're trying to do is to make concrete that serves the needs of the system that we're working on with negative environmental impact. We want to have a minimum CO2 footprint. We want to have minimum off-gassing and last as long as it possibly can in the place that we put it down. Let's go back in time. Let's look at a little bit of history. Early cements were literally volcanic ash dug out of the ground or scraped off the side of the volcano, mixed with water, and it worked like a natural cement, which was great. I mean, when I first got married, my father-in-law used to give me a very hard time about the Romans knew how to build concrete. Why don't you? Well, the products that we have to work with are a little bit different. Is that the Romans were working with natural products, we're working with manufactured products. This structure, the Duomo in Rome, fantastic structure, been around for thousands, hundreds of years. The difference being with the structure, though, is that we don't drive 18-wheelers on it, and we don't spread salt on it, and we don't expose it to Iowa weather. So, yeah, what we're doing to our concrete is a whole lot more severe than structures like this get exposed to. And that, again, is why I have a job. It's figuring out how we can make our concrete survive the environment we put it under. Early cement, the first patent was from Joseph Aston, 1824, where he made an artificial rock by burning limestone clay together and then grinding it up, adding a little bit of gypsum. The name Portland cement is because the first samples that he built of his artificial rock looked like the natural stone that was available in the Isle of Portland where he grew up. Portland cements actually haven't changed. The fundamentals of the basic compounds haven't changed. The ratios have changed, but the basic compounds haven't changed since 1824. One of the things we're doing nowadays is to add a little bit of limestone after the kiln. Let's go back one photograph. We take limestone, clay, and throw them in a furnace, and we cook them in a kiln at about 1400 degrees Celsius. It takes quite a lot of heat, generates quite a lot of CO2 because the decomposition of the limestone spits out carbon dioxide. We're getting way more efficient by using heat exchangers in towers. So the efficiency, the amount of heat energy it takes to heat the system up is getting far better. But one of the ways that we can also reduce the carbon footprint is to throw a little bit of limestone, up to about 15%, after the kiln. So it doesn't go through that heating process, it doesn't decompose. It has very small effects on the performance, and in some cases, if you're mixing it with fly ash, you get some synergistic benefit. And so we're actually getting better cement out of the mixture with a fairly significant cut in the CO2 footprint of our cements. So when you get type 1L cement made available to you, that's altogether a good thing. What about our aggregates? Once again, traditionally, stuff that we've dug out of the ground. What we're starting to look at is old concrete, we can recycle it. This is a photograph of a piece of equipment out of the Midwest, where it's basically a mobile crushing plant. It walks down the road, digs up the old concrete, grinds it back up, spits it back out, and we use that either in the new concrete or as a base for the replaced pavement that we're going to put down. Very efficient, very carbon efficient because it's not traveling very far. We're not hauling back to a crushing plant and then hauling it back to put back on the ground. Very effective use of, it's also reducing. We don't have to throw this stuff away. It's being completely recycled, and that's a good thing. More guidance from some publications that we have out there. We're starting to learn how to use fibers in concrete pavements. There are two different families, micro, very short, thin, good at preventing those early plastic shrinkage cracks, like those in the photograph where the lady was beating me with the umbrella. Macro cracks are synthetic. We try and get higher stiffness fibers. They're a little bit longer, and their prime function is when the concrete cracks, their job is to keep those cracks closed. They don't prevent cracking, but they help to keep the cracks closed. To test this out, we've built a traffic circle in central Minnesota, and in northern Iowa, we put down a test section here with a fairly high dose of macro synthetic fibers, and we didn't saw it at all. It's cracked out at about 60 feet spacing. We're keeping a close eye on those cracks to see whether or not we're still getting load transfer between the panels. But so far, the county engineer who owns this is very pleased, because one thing he does not have to do is to maintain the joints. At the moment, the last time I rode this was in November, the ride was still really good. This was an interesting, crazy experiment. We need to figure out where it takes us in the future. The other technology I'm excited about is internal curing. Curing, as I ranted about earlier, was the art of keeping the concrete wet and warm so that you can get all the hydration out of the cement that you want. Typical curing applications were traditionally adding water to the surface or spraying a curing compound so that you don't get loss of water from the surface. Both of those effects really only affect the outer surface. They don't affect what's going on in the heart of the concrete. And if you've got a low water cement ratio system that's consuming all of the water in the mixture, you can actually get some desiccation towards the bottom of the slab, and conventional curing doesn't change that. Internal curing is the idea of mixing some little reservoirs full of water. It doesn't affect the water cement ratio, but it does get sucked out of these reservoirs later on and help to cure the concrete. Therefore, there's better uniformity. The blue in the image is the affected curing benefit from these lightweight particles. And it's more uniform than doing just a surface treatment. How do we do this? Two ways. In the US, we've traditionally been looking at lightweight fine aggregate, basically kitty litter, throwing it into the concrete. The little dark spots inside this core that we've cut open is internally cured. The one that we're starting to look at is the idea of putting in superabsorbent polymers, basically the stuff that's inside diapers. It has the same effect. It's not well understood in the US, but this is the standard process in Europe for providing internal curing. Does it work? Absolutely. I took the slide out, but we built a bridge deck using this approach in Ohio. It is 2 years old and still crack-free. So when people talk to me about, it's a big problem, we don't know how to make bridge decks that don't crack. Yes, we do. We've done it. Come and talk to me if you want some help. All right, I'm running out of time rapidly. How have things changed over time? A big way things have changed is in the way we handle our materials. Cranes and buckets, we still do some. Very small ready-mix trucks. The photograph on the top right is handling the materials on a rail bed built next to the pavement as it was being constructed. Not very efficient. Nowadays, we're using large ready-mix trucks. We're pumping to get materials up to the top of the towers. Very efficient, very reliable, and we can go through high volumes relatively quickly. On the other end of the scale, volumetric trucks that can deliver just as much as you need. So things like driveways, sidewalks, where you've got small batches. You're not throwing away 8 yards, because that's all you can get in a ready-mix truck. They will mix it. It's fresh, straight into the point of delivery. So there's, in certain applications, this is a good technology to consider. Paving machines in the past, for those who didn't know, the first slip-form paving was in Iowa in the early 50s. Since then, the technology has moved quite a long way, from being 8 foot wide to 32 feet wide. The machines nowadays are full of fancy electronics, sensors. We control the rate of vibration. We adjust the shape of the pavement as on the fly. We're using 3D modeling so that the equipment can be self-steering, and we're monitoring the smoothness of the pavement. That's these bars out here as it comes out of the back of the pavement, so that we're delivering systems that are far smoother, which is a great benefit both in terms of durability and from the point of view of the riders, the customers that drive on this every day. The smoother the pavement, the less they complain. Talked about curing already. How did we do it in the past? Mud, burlap, sprinklers, none of which are very efficient. Nowadays, we apply a curing compound on the surface. If I've done internal curing, I still need to do this because I still need to keep the surface moist. Why? Because the surface is where we put the traffic. It's the surface that sees the weather, the de-icing salts, catches all of the abuse. We have to baby that surface as much as we can to get the best life out of it. All right, the next quiz. More cement makes more strength, true or false? False. Strength is everything. Well, it's structural engineers, maybe. For everybody else, false. Slump indicates quality. It used to be so 40 years ago, not anymore. False. Stronger the concrete, the more brittle it is. Absolutely not. So all of these that are beaten into everybody's heads, the standard trope messages, they're busted. The way we're doing our technology these days, those things are not true.
Hey, Peter?
Yo.
We've got a question. For the cat litter and super absorbent materials, are they fully saturated? Oops, you're advancing or going forward or backwards? Okay.
Back to that slide.
Okay. Are they fully saturated before adding into the concrete mixture so the water gets pulled out during the curing process?
For the aggregate systems, yes. And that's what makes them a little bit of a challenge because you have to have a fairly significant stockpile that is soaked for about 48 hours before you put it into the batch plant. One of the reasons I'm interested in looking at superabsorbent polymers is that the way the Europeans do it is that they put them in dry, but they add extra water to the mixture. And the polymers actually suck that excess water out during the mixing process and then release it later on. So great question and part of the thinking behind why we want to investigate these materials.
Thank you.
All right, lost my place. What do we need out of our concrete? We need strength, yes. Probably more so. We need, for some applications, we need to worry about stiffness. This building in Chicago, the strength they called for to hold the building up was 12,000 psi. But the stiffness they needed to prevent it from flipping around like a whip and getting everybody seasick at the top floors, it had to be very, very stiff. It was right in at the top end of the theoretical maximum. So controlling stiffness was actually the controlling parameter on this structure. We need bond with the reinforcing steel. We need the ability to resist cracking. We need toughness so that it's not just brittleness, it's the ability for that once a crack forms, it doesn't propagate. We need to be able to keep the water out of the system. We need the ability to resist the weather. So, it's not just strength. There's a whole lot more that we have to pay attention to when we're doing our proportioning. We're also asking for it to be faster, longer lasting, cheaper, idiot-proof, more sustainable. The bridge in the photograph, is that sustainable? In some ways, yes, it's green, it's biodegradable, it's recyclable. In other ways, no, because it's completely non-functional. None of us would put our vehicle on that. So it's not actually a bridge. It's great for the path where I walk every week, but no. How did you do proportioning in the past? This is from the 1916 version of Design and Control. 1 volume of cement, 2 volumes of sand, and 4 volumes of rock. If it was a cheap concrete, 136. I actually came across a mix built in the 1800s, so it was 134. We can do better than that. ACI 211 was written in 1991, had a process. It was linear, it was non-iterative, and generally for pavement comes up with a mixture that's far too sandy. So instead, we've developed an approach which considers the aggregates as filler and the Portland cement paste as glue. The aggregate, we have to think about the gradation. For the glue, we need to know, are we going to make Gorilla Glue or Elmer's kindergarten glue? And then we have to think about how much glue. We need enough glue to fill all the spaces left behind by the aggregates and a little bit more to separate the aggregate particles so that there's glue in between them. This helps with both the workability when it's fresh and with the strength and the stiffness and the impermeability when it is hard. The key part of this whole system is that the moment you change one of them, everything else changes. So it's a bit like solving a Rubik's Cube. It must be an iterative process in solving how to get the best out of all of our materials. We're also thinking about it in terms of the properties we're looking for and how those levers that we can pull affect those properties. And again, I've run out of time to wax lyrical about this. That can be the next work PowerPoint or session that we do. Does this approach work? Yes. 2017, contractor was using a standard mix. You can see all the bug holes and ugliness. Through the winter, we revisited, and without changing his materials, just by changing the proportions of those materials, 2018, that's the same site, same materials, same specification. He's saving himself labor because he doesn't have to pay someone to fill up all of these holes. Saving money all around. How do we test it? Again, slump strength and air used to be the default. Nowadays, we've got far better tests to tell us information about those critical properties that we're really interested in. And we're addressing this through a program called the Performance Engineered Mixtures program. We've got 18 states paying into a pooled fund to understand how do we make good concrete? How do we measure the properties? How do we measure them at the right time? You don't have to measure everything from every ready-mix truck. And how do we design mixtures that meet those requirements? It's an ongoing project. In the future, smart concrete, e-ticketing, measuring things at the right time. The picture is from a kid's TV program, and Daddy Pig here is the world's expert in concrete. And he has a magic wand. I really want one of those magic wands because in the cartoon, he's treated better than royalty, and I'm kind of jealous. So in closing, my last slide. The basics are still the same. The raw ingredients are pretty much unchanged since 1824. However, the complexity is increasing. Even since 1967, we're adding ingredients. We're opening our systems up after a few days instead of or even after a few hours instead of weeks. Curing time is days instead of weeks. De-icing chemicals we're putting down are far more aggressive. Our design life is now 100 years instead of 20 years. The knowledge base used to reside within the DOTs, not so much anymore. The smart old guys are retiring and they're not being replaced. And so the expertise is being contracted out. The photograph. It's a picture of a pavement that we were looking at in Europe. And while a bunch of experts are out there staring at this system, a truck pulled up behind us, and a guy got out and ranted and raved about why we were staring at this concrete that he had built, and he was really proud of it. Says he had been building concrete for at least 40 years. The interesting part was that he only looked about 50. But you know, over those 40 years, things have changed. It's not sand, cement, water, and rock. It's far more entertaining. And for me, it's job security. It's a lot of fun. We can spend the rest of the day talking about this. So it's more than gray, cracked, and hard. It's stuff that makes our civilization survive, and we need to understand it well. And with that, I am done.
Thank you, Peter. Does anybody have any questions for Peter? What you need to do to activate your chat pod is scroll up to the blue tab, and the drop-down will occur, and you activate your chat pod, and you can ask a question to all participants or to the panelists so that me and Peter can see it. For those of you that joined late, I'm going to take a wild guess and guess technology or wrong time zone. We are on the central time zone, so noon central time is might be not the time zone you're in. So, Peter, it doesn't look like anybody's got any questions. I did want to remind everyone we do weekly webinars. Oh, here we go. Thank you, Joseph. How do retardants work for foundations during the winter?
Do that again, Keith, sorry.
It's how do retardants work for foundations during the winter?
Well, retarders as chemical admixtures slow the system down. In winter, I'd be a little bit hesitant about them. Maybe for foundations that's okay because the system is insulated by the soil. The catch being is that the cold weather retards as well as the chemicals retarding, and you may end up not getting set for a day or two. And then you've got a fairly significant risk of plastic shrinkage cracking because it's still drying out, it's still evaporating from the surface, but it's not developing strength. I hope I understood the question correctly.
Yeah. Another question, how does CO2 emissions from concrete compare to asphalt?
I'm going to duck that one. I know nothing about asphalt. I would refer you to the trade associations.
Okay.
I'll stay out of that argument.
Okay. Okay, then. It is 1 o'clock. We do want to respect your time, both the speaker and the attendees. We appreciate you coming on board. As I was going to mention, we do have a webinar on the 10th, the 16th, the 23rd, and the 7th of August, along with a little longer leadership skills training on the 15th. Everyone is welcome to join us. I think I have everybody's information, and we appreciate your attendance. Please come back and stay safe and stay healthy and treat everyone as an essential being. Thank you, everybody. Have a good day and a good weekend. Happy 4th.
Thanks, all.
Yeah, thank you, Peter. Thanks a lot, Peter. Appreciate it.